Okay, so for practice, for each carbon, nitrogen, and oxygen on this slide, I want you to fill out the hybridization of the carbon number or nitrogen number or oxygen numbered next to the number corresponding to that carbon, nitrogen, or oxygen in the table. And I'll do the first, I'll do a couple of these with you, and then I want you to work on your own, and I'll make an entry point in the assignments for you to submit your answers. So for practice, we can determine hybridization by counting how many electron domains, and then based on the number of electron domains, writing out the hybrid geometry of that carbon, nitrogen, or oxygen. So if we start at number 1, carbon 1 has 4 bond sites, 3 bonds to hydrogen and 1 bond to nitrogen, and no lone pairs. So it has 4 electron domains. And the hybridization is sp3. Okay, let's look at some other types of, oh, I missed a carbon. Oh well, we won't worry about it. Just for practice, I will label it here. This carbon right here, which I guess I will call atom number 18, C18, has 3 bond sites and no lone pairs, and so it is sp2 hybridized. 3 electron domains, sp2. And then one other type of bond is the sp type of hybridization. So an example of the sp type of hybridization is shown at carbon 5. So if you look at carbon labeled as 5, it has 2 bond sites and no lone pairs, and so it has an electron domain geometry of 2 electron domains and is sp hybridized. I'll do one of the other ones just for practice. We can look at number 12. That's an interesting one. Number 12 is a nitrogen, and it has 2 bond sites and 1 lone pair. And so 2 bond sites and 1 lone pair is a 3 electron domains. And it is going to be, I think, a linear geometry. Linear or a type of bent. So that is, but anyways, the hybridization with 3 electron domains is sp2. Oh, for 12, not for 11. 3 electron domains. So nitrogen number 12 has 2 bond sites, 1 lone pair, 3 electron domains, and is sp2 hybridized. Now I want you guys, for homework and for practice, to fill out the rest of this table, and you can either copy it from the slide or you can make your own table, and then I'll make a place for you to submit that assignment, and it will be labeled as slide 70 practice. Okay. So just some more things about bond strength and length. We can use the type of hybrid orbital to predict the strength and length of a bond. And we can also use our periodic trends to look at the strength and length of bonds. The more bonds that we have, you should remember that as we go into multiple bonds, the more pi bonds you have, the shorter the bond is. And so the strongest and shortest bond is a triple bond, shown at the left, on the top left. So we have top left, triple bond, shortest and strongest. And then as we decrease the number of bonds between two atoms, we become longer and a weaker bond. So a double bond is weaker than a triple bond, but stronger than a single bond. It's also longer than a triple bond, but shorter than a single bond. Okay. We can look at electron density in the region of overlap to help determine whether a bond is shorter or longer. For example, the higher the S character relative to the P character, the shorter and stronger a bond will be. So if we look at an sp3 to S, and you write the ratio of S to P when you add both of the hybridizations together. So this would be a ratio of, let me get a pen, 2S to 6P, and the percentage of S would be 1/3, or about 33%. If you look at the sp3 to S bond of carbon to hydrogen, we can tell that it is shorter and stronger because it has a higher S character. And we can rate the S character by looking at the percentage of S relative to P, or the ratio of S to P. And in this case, the total S is 2 and the total P is 3. So we have 2S to 3P, or 2/3 S character. And so this is relatively 67% S, 66.66% S. Okay, and so the higher the percentage of S, or the higher the ratio of S, the shorter and stronger a bond will be. And we can do the same thing to rate the triple bonds and single bonds. If you look at the CC single bond, that is sp3 to S, sp3 to sp3, or 2/3, 1/3, 1/3. One-third S. If you look at the double bond, that is sp2 to sp2 for the carbon double bond. And so that is 1/2 S, because it's 2S to 4P. Okay, and then for the triple bond, we have sp to sp, which is a 1-to-1 ratio of S to P. And so 50% of the orbitals is S character. Let me rewrite these. If we want to look at, here we're comparing S to P, but we can also compare S out of the total orbitals. So, and that will give us the same type of idea. So we could say that this sp3 to sp3 is, instead of 2s to 6p, we could also say that it's 2s out of a total of 8 orbitals. So that would be 1/4 s. And for the sp to s, we could say that that is 2s out of 6 total, which is equal to 1/3 s. And then for the ones on the top, I like this comparison better than the other one. What we'll do is we will say that, I mean, both comparisons work, but one is just better at rating how much total S there is. So for sp3 to sp3 of the carbon-carbon single bond, then we have 2s out of 8 orbitals, which is 1/4 s. And then for sp2 to sp2, we have 2s out of 6 orbitals, which is 1/3 s. And remember, as the amount of s increases, then we're getting shorter and stronger. So 1/3 is greater than 1/4. That's shorter and stronger. And then for the triple bond, we can say that we have 2s out of 4 total orbitals, which is equal to 1/2 s. And so as 1/2 is greater than 1/3 and it's greater than 1/4, and so that should be the shortest and the strongest bond. Okay, so double bonds, they have the enthalpy of a double bond strength has been measured. A double bond has a strength of 174 kilocalories per mole, and the strength of the sp2 to sp2 sigma bond is negative 112 kilocalories per mole. And so, all right, so we have the total strength of the double bond. So sigma and pi. Sigma and pi as the top number. That looks like an H, not a pi. So sigma and pi, and we get 174 kilocalories per mole. And for the strength of the pi bond, if we take the total strength of the double bond minus the strength of the sigma bond, we can say that a pi bond is 64 kilocalories per mole, and so it's weaker than a sigma bond. But if you combine a sigma bond and a double bond, then that will be stronger than just a sigma bond. Okay. Hybridization affects bond length and bond strength. So the strongest and the shortest bond is an sp bond. sp2 bonds are going to be shorter and weaker, are going to be shorter and stronger than single bonds, but weaker and longer than sp bonds. And so make sure that this makes sense to you. Higher amount of S, then you have a stronger and shorter bond. Hybridization also affects the bond angle, so you can make the same relationship, that percentage of S. The smaller the percentage of S, the smaller the bond angle. So bond angle increases as S character increases. The more S character, the greater the bond angle. And then we have the summary of hybridization, or the amount of S, and the bond strength and length and the bond angles. sp3 bonds, which have the smallest amount of S, are going to be 109.5, so the smallest angle, but they're going to be also the longest bond and the weakest bond. sp2 orbitals, sp2 bonds are going to have bond angles of 120. They're going to have a shorter bond than the sp3 and a stronger bond than the sp3. And then bonds with sp orbitals are going to have a smaller bond angle, 180, and they're going to have a shorter length, and they're going to have a stronger bond. So please remember how the amount of S character in the hybrid orbitals that make a bond, whether it's sp3 to sp3 or sp2 to sp2, the amount of S character can help you determine how short and strong a bond is and help you determine the trend for the bond angle.